Hello, physics students. Today, our first recorded lesson ever on video. Let's see how this goes. So here we go. Today, we're going to learn about work friction. And you can't see it because it's getting contrast correct. We're going to learn about work friction today. And what we know is it's one of the four forms of energy. So far, we have PE, gravitational. We have kinetic energy. We have potential spring. Today we're going to add work friction. Now, when do we do that? It's used when we have rough surfaces. Up to now, all of our surfaces have been considered smooth, much like the Tarzan tree that he slides down or slides along. And so today we're going to talk about sections when we have rough surfaces. Now, the first thing we have to know is about the force of friction. And what do we know? Thank you. Max told us it's mu normal, just to give Max some props. So the equation we had was force of friction equals mu normal. Okay. What do you know about work? What do you know about work? This equation. Force times distance. So if you put these together, work friction, which would be W sub friction, or W sub F if you wanted to do that, is going to then be mu normal D. The mu normal is the force, the D would be the distance that it moves. Now, most of the time, what's normal? Usually, the normal is what?
Weight.
Normally the weight, which is also known as mg. Now, why might that be a good thing in our problems? Because you got an m there that you might be able to cancel with kinetic and potential. You're still going to have to use it if you've got the potential spring. Okay, so that's the new equation, the new thing we're going to do. Now, let's do a simple example, like the homework, and see if you can handle it. So we'll do this. A 5 kilogram cart starts at the top of a 45, I got to move it up a little bit, sorry, that thing, I should hide that message there, hold on, sorry, of a 45 meter frictionless hill. Now in the homework I didn't always say that, but I want you to know the hill does not have friction. The problem becomes a lot harder if there's friction on the hill. At the bottom of the hill, it crosses a section of friction with mu equal to 0.5. How far will it go until it stops? I'll slide up there a little bit so that you can get it all. What's the first thing we do then?
Equations.
Well, we could start with a picture. Let's put a simple picture on there. So here's our cart. At the bottom of the hill, we got friction. The hill is 45 meters high. Friction's mu equals 0.5. Cart's 5 kilograms. And away we go. What do we have at the start?
Potential energy.
We have potential energy, gravitational. It's not moving, so there's nothing else going on. There's no spring in there. What do we got at the bottom?
Kinetic energy.
Well, it's going to go till it stops. So if you go to the end, is there kinetic energy if it stops? No. So all you got is work friction. Work friction in almost all of our problems is the second half of the equation because it's always going to do affect what happens after. So if you write your equation, you got this. And the reason why I want you to write normal is sometimes the normal is not mg. When is the normal not mg? It's on a hill. So if we ever got a problem like this, and I would doubt they do that too much in the AP exam ever, where they put it on a hill where you'd have to use that. That's way too complex, but it could happen. So we've got to make sure. So let's rewrite this then. Since it isn't a flat plane, it's going to be this.
Do they cancel the M's?
And Artem Smolin would be very happy if we didn't put numbers in yet, because what cancels?
MV? No, just M.
M and G cancel. Because the G is the same, we don't go to another planet. So it becomes H equals mu D. So we have 45. 0.5D.
0.5D.
Divide both sides by 0.5. 45 divide by a half. 90. I always try to trick you because people divide it in half and they get 22 and a half. And they do it wrong. Make sure you divide by 0.5 when you divide by half. You get 90 meters. Is it harder than the other ones?
No, it's easier.
No. Okay. And so that's the only thing you insert. But you got to watch for some other ones. Now, let me give you just another drawn example picture. So I don't want to run out of time here today. Let me draw another example picture and see. What if we had this problem? Get it on the screen there. What if we had this problem? Tell me what we do with it. No, we won't work it out. We'll just talk about what's going to happen to it. That would be a spring in my best drawing. Yep. Okay, take a look at this picture once it comes back in focus. Take a look at this picture. See if you can understand my hieroglyphics. So what's at the top of the hill? A spring with a cart. It's 200 newtons per meter, and it's been, I forgot to put the compression on, it's been compressed 1 meter. And then you're on a 5-meter hill. When it gets to the bottom of the hill, what happens to it? It hits some friction for a set distance right here. And then it's going to still be moving after you're done. So the question we'd ask is how fast would it be going after the section of roughness? So tell me what we'd set up. This is like judging the thing. What equation would you work? PE spring. Oh, wait. Plus PE gravity, because we're on top of the hill,
Equals work force.
equals, I just did it in the wrong place. Let's try this. Sorry for the mistake. Still learning. PE gravity equals
KE. Work force plus KE.
plus work friction. Yep. And so that's where you'd go with this question for your homework. And so you'd start working the problem and see what you could do by plugging in. The nice thing about all the energy problems, they always follow the same pattern. This would have all 4 types of energy or work in them. So you got 6 questions to do. For those of you out in virtual land, they're attached to this file if you didn't come pick it up. So do your homework. And Monday we'll talk about those problems and see how you did. Have a good day. Bye.